Welcome to another video explaining the universe using the particle model. Well, today's video is on precession. This is part 2. I already have done one on the precession of the gyroscope. This is on the precession of the Earth. But before we go into that, let me advertise the book that David, my son, and I are working on, titled Principia Mathematica 2. There's a link here to our website for this book. You can go there and read about it. And this is the logo. And so we have a nice quick video showing you this video. I'm sure you can guess why why the icon looks the way it is. Already had one member do that very quickly and simply, and so that's the icon for the book. And the name of the book is Principia Mathematica 2, and you can find it at this website. Okay, let's go on. Well, yes, I've done previous videos, the gyroscope, anti-gravity. That one gets quite a bit of attention. I get a lot of continuing views on that one. Then the second one was, can the gyroscope move up? Most of us think it can move down. We know about that, but moving up, that sounds more like anti-gravity than the one on anti-gravity. The last one was on the precession of the gyroscope. And this is on precession of the Earth. So let's compare the two. And I have here a gyroscope rotating counterclockwise, and its precesses counterclockwise. Pretty straightforward. Here's the Earth. The Earth, we know, does spin counterclockwise, and you would expect that it would precess. Oh, wait a minute. Precess counterclockwise. This shows it clockwise. Well, that's not right. That's not right. So let's look at two examples. There we go. We got a nice little graphic that's moving, showing that. It'll pop up and do it again. And this is, whoever did this has the Earth going counterclockwise. You can see Australia pop off to the right. But here you see this going counterclockwise. Well, yeah, it's supposed to precess counterclockwise. That looks good, but we're looking at it from the Earth up. We're looking what I call inside up. And I'm not sure that that's the right view. Here's a different view of this. This is a celestial sphere. This sphere is very much like you get at a planetarium when you're sitting down and there's a domed surface above you. So this would look like what you would see inside a planetarium, looking up at the celestial sphere. And this is clearly looking from the outside. And we're looking down on this, and the person who drew this shows it going counterclockwise. And we expect it to precess counterclockwise, but it's not. It's going clockwise. Boy, that gets confusing. And I've said this a number of times. I go find a video that I can trust and get some solid reference point as to how I should look at these things, whether clockwise or counterclockwise, spin or precession, find out what it is. So I found this video. This one was specifically made to show the viewer how to determine and be consistent about the spin of the rotor versus the precession of the axle. This is the link. And what he's done here, he spins this up. He has a motorized way to connect a motor to this axle, spin it up one direction, reverse the battery, spin it up another direction. So he just spins it up the first time, and he lets it precess, and let's assume it's going to precess counterclockwise. We watch it. You can see it in the video. Then he grabs it, holds it with his hand, and slows it down with his thumb until it gets slower and slower, and you can see that the rotor is spinning counterclockwise when you had just seen it precess counterclockwise. Then he takes the battery, reverses it, does the same thing, and sure enough, he gets this consistent result. The direction of spin is the direction of precession. But you have to look down at the top of the rotor, otherwise you get a different view. You get an opposite view. So I drew one of my very simple drawing that David complains about. So I drew this oval, which is theoretically a rotor. I put an arrow on it to show it's going counterclockwise. Then I flipped it 90 degrees. I flipped it like you flip your hand. I'm looking at the palm of my hand, and I flipped it 90 degrees. Now I'm looking at the back of my hand. So if I'm looking at the palm of my hand and my thumb is the direction, I'm looking at counterclockwise. But I'm pretty sure that you're looking at clockwise. Depends on which way you're looking as to whether you perceive it, you see it as clockwise or counterclockwise. So it's important, the direction, and that's what the video was saying. And so the confusion can come here because here we're looking on the inside, it's spinning clockwise, counterclockwise. The Earth is spinning counterclockwise, and it's precessing counterclockwise. Well, that would be true if we were looking from the top down, but we're looking at, to me, the picture is drawn looking inside up. And therefore, it should be moving clockwise. Over here you got the, to me this was wrong. If I am looking, I'm on the inside looking up, it should be going clockwise. All right, so now we're on the outside looking down. This is moving, the Earth is spinning counterclockwise, and we're looking top down, and this is going clockwise. This is wrong, at least if you accept the point that the other video made about the gyroscope. Yeah, granted, this is not a gyroscope, this is the Earth. It could be different. So we go back and look at this picture again, and I've added two things here. To the gyroscope, I've added the vertical force of gravity. This is the net force of gravity caused by G1 particles. I call it F1 as a net force of G1 gravity. And that's where it's, whoops, I went backwards, can't do that, sorry. So the force of gravity is towards the center of the Earth on the gyroscope. So it's the Earth that causes, that is the important gravity in the gyroscope. Well, in this case, it's the sun's gravity, and I'm assuming the sun is over here to the right, and there's a force going this way. So yeah, maybe the Earth spins differently. Maybe it's not like a gyroscope. So we're going to look into that. Okay, that's the one I jumped to inadvertently. This is the one I did last time. This is the analysis I did last time, and I'm not going to go through it in any detail except to say, of course, the force of gravity is vertically down, and you can see the F1 vertically down, and it's weaker at the top stronger at the bottom, because this is closer to the center of the Earth. So the force of gravity is stronger here, weaker there. And then you have the velocity. On this side, the forces oppose the velocity. This force opposes the velocity. Therefore, this side the gravity has a stronger effect, whereas on this side, the velocity has a stronger effect. So you have a stronger effect down here due to gravity, a stronger on the right due to the canceling of opposition of velocity, which makes this the dominant vector, and ultimately you have a net force on the axle of the gyroscope in that direction. That was my conclusion last time doing what I typically do, a force analysis. Well, I flipped it 90 degrees. I flipped it to the left 90 degrees because you see it's weaker here and stronger here. So this was on the bottom, this was on the top, and I went 90 degrees to the left. I redid this, the green arrows, otherwise it's the same. Now, I can go into a lot of explanation here, but the odd thing here is that these vectors are all the same direction. There's no opposition over here. This force is pushing on this axle in this direction. This one is pushing in that direction. They all have a direction towards the east. There's no opposition. They all add pushing the gyroscope counterclockwise. I'm concluding that it really doesn't matter. It really doesn't matter with the gyroscope, or it doesn't matter which direction the force is. If it's spinning counterclockwise, it'll precess counterclockwise. If you ever watched a gyroscope, it's standing up vertically and it hangs there for a long time. Finally, when it's off, it starts precessing. If it's spinning counterclockwise, it'll precess counterclockwise. That's what I'm doing from my perspective. And as I'm going to have it fall down and go down, and it'll spin counterclockwise, even when it's horizontal, even when the gravity is perpendicular to the axis. When it's down, the rotor is this way. I'll get my hand over there. That's terrible. And the axis, there the gravity is perpendicular to the axis. When it starts out, it's in line with it. Still spins the same way. As it goes down, it keeps precessing the same way. So yeah, it seems like it doesn't matter. The net result is it spin clockwise, precess clockwise. Well, okay, you go through all that and you end up, it's wrong, this is wrong. There's something else here that was interesting. Here's the little Polaris is our current pole star. That's the North Star that we look at for navigation purposes. And it's the tail, at the end of the tail of the Little Dipper here. And if you just watch this, this goes around, it passes the bucket of the Dipper and goes over to the pole star. It goes past the bucket to the pole star. So, and it's on the right side. As we look at here, it's on that right side of that circle. You come over here, and there's no motion here, but you can see that this clockwise motion has it coming by the bucket and going to the pole star. So in a sense, it's going the same direction, even though one's counterclockwise. Of course, it's flipped. It's from the inside out, outside in. That part seems consistent. Why is that? Because the bucket is different. It's in a different position. They've changed, it looks like they changed the map itself. Talk about confusion. Yeah, and this video is exactly what I was trying to show, and I'll just go right by that one again, and that it's going by the bucket and so on. I wanted to give you a better view, forgot to jump to it. Well, let's talk about the pole stars. It's interesting. Here's 2000. Normally we generally think about AD, but there's a new phrase. It's called the Common Era. And BCE is before a Common Era. So this is the year 2000. This is the year minus 1000. It's 1000 BC or BCE, and this is around 3000. And these are the pole stars that they're saying is going to happen based on the precession of the Earth as it maps this circular pattern on the celestial sphere. And yes, it's coming by the bucket first and then the end of the tail and so on. And these are the stars that they understand were the pole stars at these eras. Thuban here is Thuban is at 3000, Kochab 1000 BCE, Polaris is our pole star. In the year 4000 it'll be Arai, then Alderamin, and then Vega, way up here. At this point, I'm having trouble with my pointer, which I've been having recently. Anyway, so those are all these are the ones that supposedly were used in history. There's none before that, probably because the alphabet didn't really start until this period of time, so there's no real written record. There may be hieroglyphics, which can be interpreted as to what's happening, but so there's no really written record, but there could be some very early written records about the pole star, and it gets better and better up till now. And so there you have it. And most people, everyone I looked at, as confusing as they are, they all seem to have the same sequence. Well, here's some pole star history from Wikipedia. In classical antiquity, Beta Ursa Minor, Kochab, was closer to the celestial North Pole than Alpha Ursa Minoris. While there was no naked eye star close to the pole, the midpoint between Alpha and Beta Ursa Minoris was reasonably close to the pole, and it appears that the entire constellation in antiquity, known as Synarsoa, Greek for dog's tail, was used as indicating the northern direction for the purposes of navigation by the Phoenicians. By the way, they invented the alphabet. Anyway, it appears that this was used. Well, that didn't sound very convincing, so I went on. Here's another link. The Phoenicians did not have a compass or any other navigational instrument, and so they relied on natural features as coastlines, the stars, and dead reckoning to guide their way to reach their destination. The most important star to them was the pole star of Ursa Minor constellation, and by way of a compliment to their seafaring skills, the Greek name for this group was actually Phoenike. I don't know if I said that right, or Phoenician. So they named the pole star, the Greeks named the pole star for these people who were so accomplished at sailing the seas. So they claim they used the stars. In the same paragraph, in the same reference, you read, historians long considered that the Phoenicians sailed only during the daytime. No pole star during the daytime. Maybe you see it once in a while. as they had to keep close to the shoreline and within sight of landmarks. At night, they therefore had to beach or anchor their ships, and this explained the proximity of the Phoenician colonies, a day's sailing distance from each other. Sounds like they didn't use it at all. Yeah, it appears that the Phoenicians may have used the pole star. But let's face it, like I say, the alphabet was invented by them. There was first ones to even write about it. And if they did, and if it was clear, we would know. Well, there is one more, a little bit better. In fact, around the year 2467 BCE, the true north was observed by drawing a plumb line between Mizar and Kochab, a fact which was the ancient Egyptians were well acquainted with. This is a fact they knew about as they aligned the Great Pyramid of Giza with it. Well, the Egyptians they had their hieroglyphs, so there should be some information, and that's probably true. But in light of everything else I've seen, I get a little bit, I say, is it a fact or not? And I didn't have the resources or time to figure that out. Clearly, my conclusion is confusion. Looking top down, we can establish a good reference for the direction of precession versus spin. And although the sequence of the pole stars seems consistent, they all seem to give it the same way. I'm frustrated by the inconsistent way the figures are presented. Further, the history is often vague in the terms it uses. So I'm asking for help. If anyone has a good reference that is not confusing and has good historical data, please let me know. I would enjoy to read it. My name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I explain more of the universe using the particle model. Thank you for your attention.